by method of multiple scales up to second order on this example that is familiar to us now. X dot plus epsilon times x times sine of t. I'll write here directly t0 plus x. Okay, so multiple scales, we will say ts is equal to the sequence. Let me see now. I'll say here n equals to the sequence of t k equals 0 to n. I haven't put curly brackets, so I just have this sequence here. Then what I will do is I will say x dot, well, let me first say xs is equal to add capital X k of ts times epsilon to the power k equals 0 to n. Okay, so this is my x0 that will go in there, and then I also have x dot, and so I will say x ds is equal to add diff xs with respect to tk times epsilon to the power k equals 0 to n. So that looks a bit long, but many of these terms will go away, don't worry. And then finally we will have dE is equal to substitute x dot equals x ds, x equals xs in dE, but I'm going to suppress that display. And then I will say dEA is equal to convert Taylor dE epsilon n plus 1 polynomial. Very good. So here is my differential equation. I had done only up to this much when I was doing first order, and the sign there was a sine square. Now this one is sine. We are familiar with this from higher order averaging with this problem, but now we are going to look at it using the method of multiple scales. Very good. At order 1 we find, see, we can do this explicitly. We can say the coefficient in dEA of epsilon to the power 0. Alright, this has to be 0. That means x0 is some function of only t1 and t2. Okay, so I will say temp is equal to, and I'll pull this out, equals some function of t1, t2. Okay, very good. What else will I do? I will say xs is equal to substitute temp in xs. That doesn't really help me too much yet. And I will say dEA is equal to expand substitute temp in dEA. But after I expand and substitute, I want to collect Alright, so now we have an order epsilon and an order epsilon square. Okay, very good. Then I say temp is equal to the coefficient in dEA of epsilon to the power 1. Alright, now you see I just have a x1 and I have these things here, and what do I need? I want let's see, I have a sine and this cosine, and I have this cosine and this sine. How does it go? I need to find the average of this. The T0 average of this has to be assigned to this, right? So temp 1 is equal to, you will see the similarity with averaging, right? Expand, substitute. We'll just temporarily put this equal to 0. And this derivative equal to 0. When we do that, well, something didn't match. When we do that, we've got this remainder term here. We need to find its average. Okay, so that part is easy. What we do is we integrate temp 1 T0 equals 0 to 2 times pi divided by 2 times pi. Let me just give it a name, AV1 equals simplify. And that's going to be 0. We knew that. And so that, well, the negative of that actually has to be equal to that. What does that tell you? That tells you that the derivative of a with respect to t1 is 0. That means a is a function purely of t2. Okay, so here we go. We say temp 2 is this. A is actually a of t2 alone. And then we say xs is equal to substitute temp 2 in xs. So all I have is this here and then something epsilon. Additionally, I say dEA is equal to expand substitute temp 2 in dEA, and then I say collect for epsilon. And of course the order epsilon term is not gone yet. All that we have is this part is still there. Okay, and what we will do is we will take the t0 integral of this, take the negative of that and set it equal to x1. So once again, temp is equal to the coefficient in dEA of epsilon to the power 1. Temp 1 is equal to expand substitute this one temporarily equals 0 in temp. Okay, then temp 2 is equal to minus integrate temp 1 with respect to t0. This is an indefinite integral. Okay, there it is. And then we say temp 3 is equal to this one equals temp 2. Then we say xs is equal to substitute temp 3 in xs. So we've got the solution up to some point. AA is something we don't yet know what it is, and this part depends on AA and T0, and this remains to be found out. And then dEA is equal to expand substitute temp 3 in dEA collect. I keep doing this. Collect for epsilon. Okay, so now the whole thing is second order, but that's all right. That's what we expect. Over here, this is the time varying part. Over here is something that does not change on the t0 time scale. once again we have this whole thing here. We say temp is equal to the coefficient in DEA of epsilon 2. I hope you see that the similarity with averaging is actually very great. Then we say temp 1 is equal to expand, substitute, temporarily we put this one equal to 0 just for simplicity, and this one equal to 0, in temp, and we calculate the average, okay, the negative of that actually. So I'll say AV2 is equal to minus, simplify, integrate temp 1 T0 equals 0 to 2 times pi by 2 times pi. Okay, you see that's the answer. And so this average has to be absorbed by this thing here. I've already put the negative because the average plus this thing has to be 0, so this is the negative of the average. And so our final slow flow equation is just this quantity. We don't have to find the W2 unless we really want to. We were interested in this part here, and so I will say final equation is equal to, and then put this here, equals previous. Okay, and that is the same as what we had from second order averaging. You will notice that an epsilon square is missing. That is because the derivative of AA is the derivative with respect to T0, which happens to be 0, plus epsilon times the derivative with respect to T1, which also happens to be 0, plus epsilon squared times the derivative with respect to T2, which means epsilon squared times this. And so it exactly matches second order averaging.